have it here. So we take a dive off the deep end and have a look at how to create a concurrent version of visualizing them a portion of the Mandelbrot set using Rust. So I thought, how am I going to cover this? Am I going to cover it from the Rust language perspective or from the mathematics perspective? And there's so much textbooks on the mathematics that I think what I'm going to do is mostly focus on how you, what are the elements you use to implement it in Rust, and some of the details or esoterics of the Rust language and how they're used to solve this problem. So get prepared. Now we jump. So I set up a simple crate to include the application, and for those that haven't been following, I've made several videos on getting started with Rust and the Rust basics. So if you'd like to, if you're not familiar with Rust, then I suggest that you watch those videos before joining in here. So just to take a top level view first, so our objective is to actually have a command line tool which will create a PNG file which will contain the grayscale graphics of the specific area of the Mandelbrot set. And what we do is that we define the pixel size of the window that we're going to use to look at the Mandelbrot's area, and then we're going to actually say the top and bottom right hand corners of the imaginary number set within the what region of the Mandelbrot set do we want to look at. So the area of the visualization, and then the actual area that we want to look at in the Mandelbrot sets. So it's like the window into the Mandelbrot. And then the last parameter is if it's parallelized or not. So we're going to have a look at what it looks like if you don't parallelize it and you do. So I'll put this code in the on my GitHub site so you can go get it. Put the link in the comments. But just a little word of also that we are depending on certain external functionality. We're using the crate called num, and then another crate called image, and then another crate called crossbeam. So we start from like the low level coming up. So this is a kind of and I want to introduce these functions so that you can actually take these and reuse these in your own application development. So here's one of the interesting facts, that actually creating a string to Boolean in Rust can be done in many different convoluted ways, but there's no absolute easiest way. But the easiest way to trick it to convert is to actually put it in a function where you pass the string, and then you say that the result will either be a Boolean or a parse Boolean error. And then when you put the string and then you say parse, then it kind of looks at the return argument and what is it going to be returning? It's going to be a Boolean type. So then it converts it into a Boolean. The parsing converts it into a Boolean automatically. That's fun. So anyways, you saw in the command line example, we do have to parse some values, and one of the values is that we want to parse a number with a delimiter and then a number. So we have a couple examples here: 400x 600 or 1.0, 1.5. And here you see the mapping, and left and right they need to be both. Those strings can be parsed from the typed from string. So let's go down here. We pass in the string, and then we say what separator it has, and then it's going to return the two different values that's separated. And and this is a completely generic implementation. So when you actually, we'll have a look at when it's actually used, then you define what is the return type you're expecting for the numbers. So we use match to find the separator, and if it can't find, then it'll return none. And then if it found sum, then it will actually have the index. And then it's pretty simple. It's going to match on two different values here, and then the index is where the separator is. So in this first case, you'll try and convert using the type defined for the function. Try and parse the left-hand value, and then it'll start do the right-hand value. And then here you see the trick of returning the left and right as a sum. Or if if there's any other kind of return, like it errors out or something, then it'll just return none. So let's see where this is used. So the easiest way to show how this works or doesn't work is to look at the test. So here you see that you actually define, okay, what is the return type you're expecting for the two numerical values. And then you have different cases. This is an empty string with a comma delimiter, and then you get nothing back and then if you only have a number on the left-hand side or the right-hand side, then it also burns out. But if you have actually 10, 20 with a comma as a separator, then you actually get the separated numbers, which will be of the type integer 32. And then here we have an equivalent floating point example. So if you have only a number on the left-hand side of the delimiter, then it will return none. But if you have it correctly formatted, then you'll get the F64 types returned. And it's kind of flexible, because then you can use it for several different numerical types. And if you would like to parse complex types, then actually now that you have that pair parsing, it's actually easy to expand that and create just the layer above it, where you want to actually return the complex data type, F64. So then you go in here and you say parse pair, and then it's a comma separated string, and then it actually takes those two values and it sticks it in a complex number, the real part and the imaginary part, or it returns none. So that's so you get the basic feature, and then you it can actually handle complex number. And then we can actually have this example of a few complex numbers here. So this is correctly formatted. So real number, comma real number, then you get it'll return a complex type with the real part being 1.25 and the imaginary part minus 0.0625. So now we get into some nitty-gritty detail. I mean, like in anybody who's dealt with game graphics development, even if you're not talking about a complex plane, and then you have this concept of a view window into the actual game plane. So, and that can be either a 2D mapping or a 3D mapping. So this is the similar concept here, where what we can see is we can see a rectangle of pixels, and then we want to say, okay, at this specific pixel point, where does it map to the which on the imaginary plane of the Mandelbrot set, where does it map to? So here we just do width and height definition, and then we actually calculate the real and imaginary location. And then if we're talking about Rust syntax, then here we can see that actually we have basically a tuple, but this can actually be more numbers, and then you can just do this syntax where you can say let width height is equivalent to that number and that number, which of course in this case is a 4. And so this is like shorthand, so you don't have to put them on individual lines. And then here we create the complex number. And here we see that when it's handling the pixel value, then it takes this here is designated the first value of the pixel, the x coordinate. And then the second value is designated by 1, which is the second value, which is the y coordinate. So you can do this kind of shorthand, so you don't actually have to put the like the x, y coordinate. Don't actually know why this is better. It seems like it's used very, very commonly in Rust code. Even if you theoretically you could actually make it more intuitive if you said pixel.x on pixel.y, but that. And then there's just a bit of a comment that as is with these view windows, you could actually have you might need to do some transformation. So like when the in our window, when it goes like from the top to bottom, then it might be in the other view window it's going from bottom to top, and it gets even more complicated when you have the 3D combination. So sometimes you're going to need to convert, transform things. And here's a little bit of a detail Rust comment logic. So when you put like 3 dashes, then it's a text you want to end up in the when you're using the Rust document generation subsystem. So then it will actually include this text in the documentation. So one of the things that you need to do is that when you're calculating is that you need to find out if the actual value is in the Mandelbrot, is included in the limits of the Mandelbrot set or not. And not to go too much into detail, but the main idea behind this escape time is that it will look at that specific coordinate, and it'll if it escapes the central region very fast, then they just say, "Oh, we won't include it." So basically, it's to one thing to see if the complex number is in the region, but then also to avoiding including too much detail, because those familiar with if you're not familiar with Mandelbrot set, the idea is that it's basically ever how much you zoom in, there's always more details to be found. So just to make sure the calculation ends in some reasonable amount of time, then you have this escape limit. Oh, now we're getting into the top level stuff. So now we render the rectangle of the Mandelbrot set into the buffer of pixels, so then it makes it visual for us. And it's in grayscale, with upper left and lower right arguments specifying the points in the complex plane that we want to actually see. So what is our viewport into the complex plane? And here I just made an extra comment about the syntax. So this is an array of mutable numbers of type unsigned character, or 8 bits. Here's the bounds, which is the pixel area that we have available and that we want to have the visualization in, and then this is the upper left and the lower left in the complex plane. So we say the row is the bounds, and here we're using this it's not using properties. I think it doesn't use properties. So here you say that okay, this is bounds is a tuple value of u size. U size is unsigned size. And then you use this concept of 0 indicating the first value and 1 indicating the second one. I still don't know why the language developers would have done this. Yeah, did we have a look at that? Yes, we did. The pixel to point we already had a look at, so here we convert it. And then we actually have a look if it's going to be included, and if it isn't, then we return none, otherwise we actually take it. And we scale it to be the grayscale value. Now we finally get to the main function. So this is the top level, which glues everything together. So we pick up the arguments, and then we check if there is the correct number, and if it isn't, then we actually visualize like what is the command format to be used. And then we parse all the values. This is using this parse pair, parse complex, and string to boolean functions that I already showed. And then it's using this expect to cover the situations where the parsing will not work. And then we get the bounds in the upper left and the lower right, which is the rectangle locations in the complex plane, and then if it's going to be a parallel calculation or not. And then we here we use a vector micro, that is going to create a zeroed out vector starting from bounds 0 to bounds 1. That's the size multiplication. And it's a mutable array, mutable vector. And then there are very many different ways to actually time things, but I use this instant object. So then you can actually say, okay, then start is now. And here we have this parallel. So if it's non-parallelism, then it just uses this render functionality, where it passes in the mutable array of pixels, and then it gives the bounds on the left and right. However, if it's a parallelized calculation, then you need to say, okay, how many threads do you want it? So how many parallel processes do you want running? So this could use 8 cores or virtual cores hyperthreading, and that depends on what CPU OS you have. You can also, you don't need to hardcode it. There is a library or a crate called non-CPUs where you can actually, it'll give you how many cores, physical cores your processor has, and then how many hyperthreading cores does your processor have. So then you can decide, okay, how many threads do you want to fire off. And then it's going to divide the actual viewing window, or the pixelized viewing window, into bands, depending on the number of threads. And to do that, it's going to create an array of vectors, rows per band times bounds elements. The last chunk may contain fewer rows, but each row will contain the same number of pixels. So that's automated. This is this chunk pixels chunk smut functionality. It'll automatically build you these blocks. And then here we come to this multitasking threading syntax of Rust. So first it's going to use the closer expression. So we read this like, so it's like to call closure with argument spawner, and do not return until the threads created within are completed. So this is similar to many other programs where you put a lock around what you're going to multitask, so that it doesn't get eaten up by other stuff, and you don't let it prime exit before it's done. And then here it's just going to iterate forever. It's going to start the process of calculating the bands. It's going to fire them off, and then it uses this spawn move closure, so-called closure syntax, to actually trigger. And as you see, it's the exact same render function. So we haven't needed to go in and reprogram the render functionality to make it parallelized safe. We just use this Rust concept of the cross beam closure spawner or scope and spawn logic. So then this is where Rust is delivering on its promise, where it says that when you implement multi-threading code, there's no way you can end up in a deadlock situation or a race condition or values being over, like two individual executing sub-calculations riding on top of each other, or preliminary exiting of the procedure before it's finished. all the kinds of different things that you see in C and C++ that the language cannot itself guarantee. Rust, if you make this logic non-parallelizable, you will actually not succeed in compiling, because the compiler will give you a really hard time and not permit you to do stuff that the compiler will guarantee that the compiled code is can be executed safe, which I think is kind of cool. And then here is just to get I pick up the elapsed time and then print it out. So let's see what this looks like when we execute it. So I'll just run the test, because actually in the test command I've actually included this, that it runs it just like it would from the command line. And one version it'll run without parallelism, and the other one it will run with parallelism. So there we go. And basically, since we were talking about parallelism, then I did run the other tests also. So as you see here, it's like the test parse complex parse pair and point to pixel. Then let's see, can I see it here? So here is. Yeah, that's a bit, because I have to keep the window a bit smaller for a video, of course, but you can see here that the last parameter is true, so this is the parallelized version. So that's 1.4 seconds, and then the non-parallelized version is 4 seconds. So that's already quite a difference, and there are ways to optimize further the parallelization. And then, of course, the interesting thing is that did we get a Mandelbrot set of any kind? So let's have a look at that. So just make it a bit bigger. So here's the Mandelbrot set, the region of the Mandelbrot set that we decided to visualize. And as I said, that it's in grayscale format. So it's not that difficult to turn this into a colorized, also color scaled image, and do all kinds of other tricks. But it's not part of this presentation. I just thought I'd show some of the when you're going to parallelize it, to show the low level routines, show how they're combined and used in the main level, and then see how easy it is to using Rust syntax to actually parallelize it without actually having to do any extra work at all. And the compiled result is guaranteed to be thread safe. So I hope you enjoyed that. It was a bit of a tour over more complex code than we usually have had a look at previously. But as I said, I'll upload it to my GitHub site, and then you can pick it up and use it as building blocks if you feel it's interesting. And I tried to add quite a lot of comments also, so that it actually highlights the different Rust features that are not so commonly existing in other programming languages. So if you're like, if you're kind of new to Rust, then it's easier for you to, then you're pointed to okay, what is significantly different, or it doesn't work the same as in other languages. So anyway, we will continue the investigation of the Rust programming language in other videos also. So I'll see you in the next one. So if you're wondering where the image came from, then that's just the last function in this in main. So it's this one here, which is the library function. Write images, so that you can actually write many different formats, like in any other. There's a library for handling, so you can do grayscale, color, all kinds of stuff. So then it just says the file name, and then it gives the pixels, and then it defines the bounds, and then this is just to capture any error that happens when it's creating the image.